Hello everyone, and welcome back to Tech Adventure. Hope you're doing great and staying sharp in your journey of software development, embedded systems, and interview preparation. In previous videos, we covered popular communication protocols for microcontrollers and peripherals like ADC. We also understood concepts in their questions-answer topics like RTOS, Top 50 Real-World C and C++ interview questions, solid principles, common design patterns, and other key interview Q&A. If you missed them, I highly recommend checking out our previous videos. Today, we will be commencing a new series dedicated to artificial intelligence, machine learning, and deep learning. This decision was made in response to several comments received on this topic. Given the increasing integration of these concepts into daily workflows, it seems that this subject matter holds significant relevance to our current environment. We will begin with a comprehensive overview of AI, ML, and DL, exploring their practical applications and how it is utilized by both software and embedded developers. Let's dive in.
Welcome to the Deep Dive, where we really try to break down complex topics based on some solid source material. And today, we're diving into something absolutely huge, artificial intelligence. It's everywhere. We've pulled together a great set of resources for this one, basically a collection of really well-structured questions and answers covering AI, machine learning, deep learning, the whole lot. Our mission here for you is to cut through all that jargon, make sense of it all, and show how AI isn't some sci-fi dream anymore. It's here, it's affecting your life, and definitely changing the game in software development.
Absolutely. We want to make this journey really clear. We'll break down the core ideas, look at how it's actually being used, the tools involved, and even touch on the ethics and what's coming next. It's really about getting you informed quickly and clearly so you really understand where things stand with AI today.
Okay, let's get into it. AI. We hear this term, all the time. Movies, news, but for those of us watching the tech space, we know it's maybe not quite like the movies paint it. So what is AI really today?
Well, the core idea, fundamentally, it's pretty straightforward. It's about building machines that can, think, learn, make decisions, basically mimicking human intelligence in some way. But what's really key here, I think, is that it goes beyond just following fixed rules. It's not just pre-programmed responses. AI systems analyze massive amounts of data, find patterns, and then actually get better over time. It's adaptive.
Adaptive intelligence.
Yeah.
Okay, so it learns and evolves. But then we hear machine learning, ML, deep learning, DL. How do these all fit together? Are they just different words for AI, or is there a structure?
Yeah, that's a super important question. That's where a lot of confusion comes in, right? Think of it like this. AI is the really big umbrella, the whole field trying to make machines smart, problem-solving, reasoning decisions. That's AI. Now, machine learning, or ML, that's a major part of AI. It's a specific approach within AI where machines learn directly from data. They learn without you having to write code for every single possibility. So building a spam filter, maybe you don't list every spam word, you show it lots of emails labeled spam or not spam, and the ML model figures out the patterns itself.
Okay, so ML learns from examples.
Exactly. And then deep learning, DL, that's an even more specific subset inside machine learning. This is where a lot of the really exciting stuff like large language models or amazing image recognition comes from. Deep learning uses these things called neural networks with many, many layers, very loosely inspired by brain structure to find incredibly complex, subtle patterns in data, things humans might even miss.
Ah, I see. So it's like nested dolls. AI is the biggest, ML is inside, and DL is inside ML.
That's a great way to put it. AI is the goal, ML is a primary method, and DL is a very powerful technique within ML that's driving a lot of the recent breakthroughs.
Got it. That clears things up. But when we talk about AI now, we're not talking about conscious robots from the movies, are we? How do we categorize the AI we actually use versus those future ideas?
Right. Another crucial distinction. What we have today, overwhelmingly, is what we call narrow AI. Sometimes people call it weak AI. This kind of AI is designed and trained for one specific job. And it can be brilliant at that job. Think Alexa or Google Translate or an AI that plays chess better than any human.
Okay, so task-specific.
Exactly. They're amazing in their lane, but totally lost outside it. Your chess AI can't order you a pizza, right?
Right, makes sense.
Then you have general AI or strong AI. Now that's the sci-fi goal. An AI with human-like intelligence that could learn and apply itself to any intellectual task. Understand context, reason abstractly.
But that's still theoretical.
Oh, absolutely. It's a major research goal, but we are definitely not there yet. And then way out there is super AI, purely hypothetical AI that would surpass human intelligence across the board. That's really just speculation at this point.
Okay, so mostly narrow AI today. But even this narrow AI is having a massive impact. Why is it suddenly so vital across almost every industry? It feels like it exploded.
Well, it's a confluence of factors, really. More data than ever before, much more powerful computers, and breakthroughs in those algorithms, especially deep learning. But the why, it's important. It automates repetitive stuff, sure, but often with better accuracy and speed than humans. That means huge efficiency gains, lower costs. Plus, it helps us make sense of all that data for better decision-making. And critically, it's enabling totally new products and services. Think self-driving tech, smart assistants, personalized medicine, things that just weren't possible before.
You really do see it everywhere now. Netflix recommendations, fraud alerts from the bank.
Exactly. Voice assistants, medical diagnosis aids, chatbots, it's becoming a foundational layer.
Okay, so we've got the what and the why. Let's dig into the how. How did these AI models actually learn? You mentioned learning types earlier.
Right. There are three main styles of learning. First is supervised learning. This is like learning with a teacher or maybe flashcards. The AI gets data that's already labeled with the correct answer. So input and the desired output. It learns the mapping between them.
Like predicting house prices, you said, with size, rooms, and the actual past price.
Precisely. You give it the features and the known price, and it learns that relationship to predict future prices. That's supervised. Second is unsupervised learning. Here, there's no teacher, no labels. The AI just gets a bunch of raw data and has to find structure or patterns on its own.
So finding hidden groups or something.
Yeah, exactly. Like customer segmentation, grouping customers based on buying habits without knowing the groups beforehand. The AI discovers the clusters. And the third one is reinforcement learning. This is more like learning through trial and error. An agent tries actions in an environment, gets rewards for good moves, penalties for bad ones.
Like training a dog, almost. Or learning to ride a bike.
Kind of. It learns the best strategy over time to maximize its reward. This is how AI learns to play complex games like Go, or how robots learn to walk or navigate.
Okay, supervised, unsupervised, reinforcement. Got it. So within those, how does AI tackle different kinds of problems, like telling cats from dogs versus predicting a stock price?
Good question. We often categorize the task the AI performs. Classification is about assigning an input to a specific category. Is this email spam or not spam? Is this picture a cat or a dog? Predefined bins.
Okay.
Regression, on the other hand, is about predicting a continuous number. What will the temperature be tomorrow? What's the likely price of this house? It's predicting a value on a scale, not a category.
Right, a specific number.
And clustering, which we mentioned with unsupervised learning, is about grouping similar things together without knowing the groups beforehand. Finding those natural groupings in the data itself, like finding customer segments.
Classification, regression, clustering. Makes sense. Now, the really exciting part for many neural networks, you mentioned they're inspired by the brain.
Yeah.
How do they actually work in simple terms? And why so many types?
Okay, simple terms. Think of them as layers of interconnected nodes or neurons. Each connection has a weight, like a strength level. Data comes in the input layer, gets processed through one or more hidden layers, and in those hidden layers, the network does complex calculations, combining inputs based on those connection weights. Then an output layer gives the result.
The learning part is adjusting those weights.
Exactly. During training, the network compares its output to the correct answer, if it's supervised learning, and adjusts all those weights slightly to reduce the error. It does this over and over millions of times until it gets really good at the task.
Wow. Okay. And the different types, CNNs, RNNs.
Right. Different network architectures are better suited for different kinds of data. CNNs, convolutional neural networks, are amazing for images and video. They have special layers that are good at detecting spatial hierarchies, edges, shapes, objects. Think facial recognition, self-driving car vision.
Okay. CNNs for seeing.
Yeah. RNNs, recurrent neural networks, are designed for sequences data where order matters, like text or time series. They have a kind of loop, a memory that lets them consider previous elements in the sequence.
Like understanding a sentence requires knowing the words that came before.
Precisely. And LSTMs, long short-term memory networks, are a more advanced type of RNN that are particularly good at remembering information over longer sequences. Really important for complex language tasks.
Okay. And transformers. They seem to be everywhere now, like with GPT.
Ah, yes, transformer models. They're kind of the current state of the art, especially for language. They use a clever mechanism called attention. Instead of processing words strictly in order, attention lets the model weigh the importance of all words in the input relative to each other, no matter how far apart they are. This makes them incredibly powerful for understanding context, translation, and generating text like ChatGPT does.
That attention idea sounds key. So AI isn't just understanding anymore, it's creating. Tell us about generative AI.
Yeah, generative AI is a huge leap. These models don't just analyze existing data, they learn the underlying patterns and can then generate brand new, original content. Text, images, music, code, content that often feels convincingly human-created.
Like the examples you mentioned, GPT for text.
Exactly, GPT models for text generation. Then you have image generators like Stable Diffusion or DALL-E creating incredible pictures from text prompts, even music generation models like Jukebox. It's AI as a creative partner almost.
That's incredible. And you mentioned something called embeddings are important for these models. What are those?
Right. Embeddings are fundamental. They're a way to represent things, words, sentences, images, even products as lists of numbers, basically vectors, in a mathematical space. The clever part is that things with similar meanings or characteristics end up closer together in this space.
So the computer can kind of understand relationships mathematically.
Exactly. The classic example is king, man plus woman equals queen. The vectors capture semantic meaning. This is crucial for search engines understanding intent, not just keywords, or for recommendation systems suggesting things you'll actually like. It's how machines handle meaning.
Okay, this is starting to paint a clearer picture. Now let's bring it to the developers listening.
Yeah.
What are the main tools, the frameworks they're using to build AI applications?
Sure. In the deep learning world, the two big players are TensorFlow, developed by Google, and PyTorch from Meta, Facebook. Both are incredibly powerful and widely used in research and industry.
TensorFlow and PyTorch. Okay.
For more traditional machine learning tasks, maybe not deep learning, Scikit-learn is extremely popular. It's very user-friendly, great library. And another one worth mentioning is ONNX, which stands for Open Neural Network Exchange. It's important because it lets you, say, train a model in PyTorch and then run it using a TensorFlow runtime, or vice versa. It helps with compatibility.
Gotcha. So with these frameworks, we're seeing tools like GitHub Copilot and ChatGPT really change things for developers day to day. How are they transforming that workflow? It feels like a massive shift.
Oh, it's absolutely huge. It's not just a small productivity boost. It's changing how people code. AI coding assistants like GitHub Copilot or Tabnine, Amazon Code Whisperer, they work right inside your editor. As you type, they suggest lines of code, entire functions sometimes. It's like having a super fast pair programmer constantly giving you relevant suggestions.
Wow. And ChatGPT.
ChatGPT and similar large language models are acting like universal assistants. Devs use them for, well, almost everything around the code, too. Getting explanations for error messages, brainstorming approaches to a problem, generating boilerplate code, summarizing documentation.
Can you give some specific Copilot examples? How's it helping in practice?
Sure. For documentation, you can literally ask it, write a doc string for this function, or generate a README for this project, and it does a pretty good job. Need to understand some weird legacy code? Ask Copilot Chat to explain it.
That alone sounds amazing.
Right. For design, you can prompt it like, Generate mermaid code for a class diagram representing, and paste it right into your docs. For implementation, it helps scaffold new files, suggests refactoring improvements, even helps apply changes across multiple files. And testing, huge help there. It can write unit tests, suggest edge cases you might have missed, create basic integration test setups. For debugging, you can paste in a stack trace and ask what likely caused this. It can often pinpoint the issue and suggest fixes.
So it's touching almost every part of the development cycle.
Pretty much. It's becoming deeply integrated.
Which leads to the bigger question. What does this mean for the future of engineering work? It's not just coding faster, right? It sounds like the job itself is evolving.
Definitely. It's less about just typing code faster and more about shifting the focus. Think about Agile and DevOps. AI can potentially help predict sprint velocity, auto-generate tests in CI/CD pipelines, monitor production logs for anomalies. The key idea is that Copilot concept. If AI can reliably automate, say, 50–60% of the more routine boilerplate tasks,
Then engineers have more time for.
for the harder stuff, complex system design, innovation, strategic thinking, cross-team collaboration, mentoring, the uniquely human skills, it elevates the role, focusing it more on high-level problem-solving and creativity.
Okay, that's a powerful vision. Now, we've mostly talked about AI running in the cloud or on powerful machines, but it's also moving into tiny devices, right? Edge, AI, AIoT.
Yes, absolutely. Edge AI, or AIoT, artificial intelligence of things, is a really exciting frontier. It's about running AI models directly on the device itself, often small, low-powered devices, without necessarily needing to talk to the cloud constantly.
Why do that? What's the benefit?
Several big ones. Speed. The decision happens right there, instantly. Crucial for things like self-driving cars, privacy. Sensitive data, like from a camera, might not need to leave the device. Reliability, it works even if the internet connection drops. Bandwidth, you're not constantly streaming huge amounts of data.
Makes sense. What kind of applications use this?
Oh, lots. Smart cameras doing on-device object detection, voice assistants doing local wake word detection like, hey, Siri, autonomous drones making flight adjustments, medical wearables analyzing vital signs in real time, industrial sensors predicting machine failure.
So even smaller than that, I hear about TinyML. What is that specifically?
TinyML is taking edge AI to the extreme. It's about running machine learning models on microcontrollers. Those really tiny, cheap, low-power chips found in billions of devices. Think smartwatches, fitness trackers, environmental sensors, appliances.
Wow. How do you even run AI on something that small?
It's a huge challenge. These chips have tiny amounts of memory, very limited processing power, and often run on batteries for months or years. So you need extreme optimization.
Like what kind of optimization?
Key techniques include quantization using smaller numerical formats, like 8-bit integers instead of 32-bit floats, which dramatically shrinks the model size and speeds up computation. Pruning, removing unnecessary connections or neurons from the trained model, and very careful memory management. There are specialized frameworks too, like TensorFlow for microcontrollers, Edge Impulse, and tools from chip manufacturers like STMicroelectronics, all designed for this ultra-resource-constrained environment.
Incredible what's possible. So stepping back a bit, beyond just coding, how does AI boost efficiency for, well, pretty much everyone?
It acts like a force multiplier for productivity. Think about auto-suggestions, catching errors early, reducing time spent debugging that applies beyond just code. Faster prototyping of ideas, whether it's code, design mock-ups, or even writing outlines. Personalized learning tools, AI tutors adapting to your pace, automating repetitive tasks, generating reports, summarizing meetings, writing basic emails, even aiding decision-making by analyzing options or simulating outcomes. It's about offloading cognitive load for routine stuff.
It sounds incredibly powerful, but that leads to the other side of the coin. What about the ethical concerns, the risks? This can't all be straightforward.
Not at all, and it's crucial we talk about this. There are significant ethical considerations. Bias is a huge one.
Yeah.
If the data used to train an AI model reflects historical biases, gender, race, etc., the AI will learn and potentially amplify those biases in its decisions.
Leading to unfair outcomes.
Exactly, which ties into fairness, ensuring AI systems treat different groups equitably. Then there's the impact on jobs. AI will likely automate some tasks, potentially displacing some roles, while also creating new ones that require different skills. Managing that transition is key.
So how do we use it responsibly?
It requires conscious effort, transparency in how models work and make decisions, regular audits for bias and fairness. Crucially, maintaining human oversight, especially for high-stakes decisions, the human-in-the-loop approach. We can't just let AI run critical systems unchecked.
And for software engineers specifically, are there unique risks with using AI tools like Copilot so heavily?
Yes, there are risks to be aware of. Over-reliance could potentially lead to reduced critical thinking or a shallower understanding of the underlying code. AI-generated code might also contain subtle bugs or security vulnerabilities that are harder to spot. Vigilance and code review are still essential.
Okay, a lot to consider there. Looking ahead then, say, the next 5 to 10 years, what big trends do you see for AI, especially its impact on software engineering?
We'll definitely see more edge AI running locally on phones, cars, appliances becoming much more common. The LLMs like ChatGPT will get even smarter, developing a much deeper understanding of code structure, logic, and intent.
So even better coding assistance.
Absolutely. And potentially moving beyond just code generation to assisting with software architecture design, suggesting patterns, analyzing trade-offs. I really think that vision of AI becoming a true co-pilot for every engineer will solidify. Automating maybe 50–60% of routine work seems plausible. And again, that means engineers shifting their focus towards higher-level innovation, complex problem-solving, and creativity. The nature of the job will continue to evolve.
Wow, what a journey we've taken. From the basic definitions through how AI learns and creates, the tools, the edge, the ethics, and right into the future. Hopefully this deep dive has really helped you get a solid handle on AI.
Yeah, connecting all these pieces, it's clear AI isn't just another tool. It's becoming fundamental, woven into the fabric of how we create and interact with technology. It's really reshaping things.
So as we wrap up, here's something for you to think about. If AI does automate, say, more than half of the routine tasks in software development, what purely human skills, maybe creativity, critical thinking, empathy, strategic planning, can become the most valuable in that future? What should we be cultivating? Definitely something to ponder. Thanks so much for joining us for this deep dive. We look forward to exploring more fascinating topics with you next time.
Thank you for watching. Please like, share, and subscribe to our channel for more exciting updates. Your support motivates us to create valuable content. Share your feedback or topic requests in the comments. See you in the next deep dive learning or interview session.